Hi guys. Okay, so we're into solutions, and we're going to really focus today on solutions in water or aqueous solutions. So let's start with water.
Do you guys want to see a little magic? Well, not magic, it's science, but the two are almost interchangeable. I'm going to show you how you can bend water at your will. We're going to start off small, just so you can grasp the concept. Water, or H2O, is a polar molecule, meaning that it contains both positive and negative charges, the positive charge coming from the hydrogen, and the negative charge coming from the oxygen. Therefore, water itself attracts to negative and positive charged particles. Now, for this demonstration, we will be using a comb. Now, when you rub your head with the comb, it collects electrons from your hair. Remember, there's electrons in everything. Since electrons have a negative charge to them, the comb now has a negative charge. All you have to do is put the comb close enough to the water and it will bend right before your eyes because the positive charge in the water molecule is trying to attract the negative electrons. Now, you know you can bend water with the comb. Is there any other objects you think you'd be able to bend water with? If so, let us know below and we'll be sure to update you as soon as we hear from you.
Okay, so we talked about water being partially charged, right? And this idea that gives it some power, right? We can bend it, but we're going to talk about water's power to help things dissolve. Okay, so let's get started. So we're going to focus on ionic compounds first. Ionic compounds generally are metals with nonmetals, or often metals with polyatomic ions. And because water has partially charged sides, as we just saw, it can pull apart many ionic compounds. Opposites attract. And it can make them dissolve and even dissociate, like fully split apart into their original ions. However, some ions are held together so strongly that water is not strong enough to pull them apart or dissolve them, and they remain insoluble. So we've learned table F. Let's keep going with that. Okay, let's keep going. And let's see if I can get back into present mode. Okay, so table F we've learned. This is group 1 because we often have to go look at group 1. Let's take a look. CaCO3. Always start with the anion first. Carbonate. Carbonate is here and is usually insoluble. Okay? Notice we start with the rule, not the exception. Are there any exceptions to when carbonate is insoluble? Yeah, when it's with a group 1 or ammonium. Well, calcium is definitely not ammonium, and calcium's also not in group 1. So it's not an exception. So calcium carbonate will be insoluble. Let's keep going. NaNO3. Again, start with the NO3. Go find nitrate. Okay, hopefully you found it here. It is soluble. There are no exceptions. So it can be paired with anything and it will still be soluble. Li3PO4. Again, I'm looking for the PO4, the phosphate is where we start. Find your phosphate. Here it is. And is Li one of the exceptions? Well, Li is certainly not NH4, but is Li a group 1? Yes. So this is an exception. Normally, phosphate's insoluble. The exception makes it the opposite, soluble. Okay, let's keep going back. Computer's loading a little bit slowly. Let's see if we can jump ahead here and present. Okay. Look for the SO4, sulfate. Here it is. Sulfate is usually soluble. Is Ca an exception? Yes. So even though it's usually soluble, because calcium's the exception to the rule, it makes it the opposite, insoluble. And GSO4, try this one. We just were at SO4, so we're right here. Is Mg an exception? No, not in the list. So it is, oh, sorry, that one's bad. It should be not PO4, SO4, and SO4 will be soluble. So ignore that there. Sorry about that. Chromate, CrO4, usually insoluble. Is lead 2 one of the exceptions? No, lead 2 is not a group 1. Lead 2 is not in the list. So it's insoluble. NH4OH, hydroxide. Find the hydroxide. Here it is. It's usually insoluble, but NH4 ammonium is an exception, flipping it and making it soluble. AgCl. Again, we always start with the anion. Go find Cl, chloride. Here it is. And Ag plus is an exception. Usually it's soluble. The exception makes it insoluble. NaCl. We were right here already. Chloride is soluble. Na is not one of the exceptions. It's always soluble. When things are insoluble, what does that look like? Well, it forms a precipitate, okay? A solid precipitate. And we often will see this in double replacement reactions. So that's what we're going to look at next. When they do form a precipitate, you can actually filter and capture that precipitate, as we learned when we learned separation techniques last week. So let's take a look at a double replacement. In a double replacement, the cations and anions switch places. So like AB, CD will have a new partner, AD, CB. And we can take a look at this real world example. Lithium sulfate and barium chloride will switch. This is 2 compounds, so it is a double replacement. Barium will now be with the sulfate ion, and lithium will be with the chloride. They both started off soluble and aqueous. Let's see what the product will be. First, let's start with barium sulfate. So go find sulfate. Hopefully you found it here. Is barium an exception? Yes. So what does that mean? Sulfate is usually soluble. Barium being the exception makes it insoluble. So this will be a precipitate or a solid. Let's do lithium chloride. Chloride is here. Lithium is not one of the exceptions. That means that chloride will stay soluble. Okay, so what does that look like? Well, if barium sulfate will precipitate, that means it's going to become a solid precipitate. And LiCl, lithium chloride, is soluble in the water, so it will be aqueous, AQ. So that's what you would put in a double replacement reaction. You can predict which things will be the solid precipitate. You can make a prediction. And this is actually used in the real world, this particular piece, barium. Okay. Barium salts are generally toxic, but barium sulfate is insoluble, as we just found out. It's so insoluble, it can be used to diagnose stomach and intestinal problems without being absorbed into the tissue. It's so insoluble, your body doesn't even absorb it. Okay. An outline of the digestive organs appears on x-rays of patients who have been given a barium milkshake or barium enema, a suspension of very fine barium sulfate particles in water. Again, it's so insoluble that it travels throughout your body and doesn't really interact. It stays insoluble. And you're allowed, it helps doctors be able to see beyond their eyes. Okay, so we did study more than that. We also studied things like dissolves like. We learned that like dissolves like with polarity. And let's take a look at our next video. Okay, let's watch the video.
Have you ever wondered how sugar dissolves in water? It actually has something to do with the way the water molecules interact with the sugar molecules. When you first pour sugar into a glass of water, the sugar is still visible. This is because the sugar molecules have only just been exposed to the water molecules. They have not had much time to interact. The sugar molecules are still attracted to each other. As the sugar is stirred into the water, the sugar seems to disappear. But it doesn't really disappear, does it? No. Both the sugar molecules and the water molecules are still present. The reason the sugar seems to disappear is because the sugar molecules are more attracted to the water molecules than they are to each other. When the water is stirred, the sugar molecules mix with the water molecules. The water molecules insert themselves between the sugar molecules and begin to surround each individual molecule. The once clumped together sugar molecules are now more attracted to the water molecules, which is why they easily separate from each other.
And also notice sugar, which is covalent polar, and water is polar, like dissolves like. But also notice the difference because in ionics, that particle will be further split and dissociated. That's not going to be happening with the covalent ones. Covalent particles will spread out and be attracted to the water, but will not break further and dissociate. And we'll talk more about that later in the week. Let's keep going.
When the water molecules surround all the sugar molecules, the sugar is dissolved.
Okay, so like dissolves like, polar dissolves polar, nonpolar will dissolve nonpolar, and polar and nonpolar will not dissolve in each other. Like dissolves like has to do with covalent molecules. Covalent molecules can be polar or nonpolar. And like dissolve like tells us polar will dissolve in polar, nonpolar will dissolve in nonpolar, and polar and nonpolar will not mix or dissolve well. So let's take a look at this experiment. Hey guys, Miss Redican here, and we're getting ready to do a short experiment that you can do with me at home. All of you should have your lab envelope, and you want to find your mole dollar. Okay, it's worth $1,000,000. I know. Okay, so let's take a look down here. Just take your mole dollar and water in a bowl. It doesn't have to be a beaker, just plain old water. And put your mole dollar in. And give it a little stir. Okay, so you should be noticing something, observing what is happening, and please again try this at home with your mole dollar. So what does this tell you about what the mole dollar is made of? That's the question. Okay. So it dissolved in water. We know water's polar. Think through that like dissolves like. Okay, so let's go through, just review what we've learned today. We've learned about water being partially charged and able to pull apart some ions, not all. If it's ionic, we can take a look at our table F and be able to make predictions of which things will be soluble and which things will be insoluble. We've learned that things that are insoluble precipitate. In fact, you can even capture that precipitate with a filter and separate things that way. We've also learned that this relates to double replacement reactions, and we can predict what the products are going to be. And we've also reviewed like dissolves like, which deals with covalent particles and covalent molecules and how they dissolve. So ionics and covalence have different rules. We're going to keep working on this throughout the week. Good job, guys. Thanks for hanging in there.